you have some lines you see on this picture, but these lines are equipotential lines. Okay, that means you see this line is a curved line. It's not a straight line, it's curved. It's curved, and it says 3V. Well, V is some potential. It can be 1 volt, 2 volts, whatever, but it's 3V, so it's just scaled by V. All the points on this curve, it says, has the same potential of 3V. Okay, and all the points on this curve, on the second curve, on this one, has the potential 2V, right? And this one has the potential V, this one has the potential 0, and the last one, fifth one, has the potential minus V. Okay? If a line, a collection of points, has the same potential, when you connect these points as a line, or this can be a surface in 3 dimension, you call this region as equipotential line or equipotential surface. Okay, so in fact these lines are equipotential lines. Why? Because on each line all the points have the same potential. You may ask, okay, if there is some potential, where are the charges? Charges are somewhere, it's not here. But whatever the charges or the charge distribution, these charges or charge distribution creates a potential of 3V on this line. That's the meaning, okay? On this curve, wherever these charges, we don't care about the charges, these charges create a potential of 3V on these collection of points. I think this is clear, right? And similarly, since this one has a different distance to the sources, wherever, this has 2V, this has V, and this has 0 minus. And one other thing is, I don't know if, I think this is on my YouTube videos, and maybe yesterday also I shown this video. If we have, if you are given not the charge distributions or the source charges, but the electric field at some region of space. This is your electric field, okay? These are electric field lines. Okay. Then with these lines, in fact, you can draw equipotential lines. If you know the electric field lines, right, you can draw the equipotential lines with this information of electric field lines. One unique property of equipotential lines are such that all equipotential lines are always crosses the electric field perpendicularly. If you have a uniform electric field like this, then the equipotential lines, let me draw with a different color, are these lines. Okay? These are equipotential lines. Let's call this one 1, 2, and 3. Okay? Forget about this picture. You only concentrate on this one. If these are electric field lines, then these red lines are the equipotential lines. If these are straight lines, the equipotential lines are also straight lines. But they always crosses the electric field perpendicularly at every point. At every point, they must cross the electric field perpendicularly. If one has, let's say, a potential of 3V, right? All these points on this line will have the same potential of 3 volts, let's say. But since this is a different line in compared to line 2, line 1, this will have a different potential, not 3V, but let's say 2 volts. But again, every point on this line will have the same potential of 2 volts. Again, if you think this one 1 volt, that's the third one, this has a different potential than this one or this one, but the thing is, every point on this line has a potential of 1 volt. Okay. If you have a curved electric field vectors or electric field lines, and you can again draw the equipotential lines accordingly. Again, you draw the equipotential line, for example, this, and here. You see this is one equipotential line because it crosses the electric field lines perpendicularly at every point. Again, you may draw a second equipotential line. You may draw as many equipotential lines as you want. It's up to you. It's as you wish, whatever. Okay, this will be a second equipotential line. This is another equipotential line. If your electric field lines are curved, you see the equipotential lines will also be curved. If the electric field lines are straight, then the equipotential lines will be straight. Okay. What about equipotential lines? Let me show this in another blank page. You think of a charge Q minus charge Q, let's say, makes this. So this charge, point charge, nothing else around, creates an electric field, right? The electric field lines are always radially ending on negative charges. If this were a positive charge, then the arrows will point away. You see, all lines are merging at one point at the source. And if I ask you to draw the equipotential lines for this point charge configuration, you can easily draw these as concentric circles. So you draw such a line so that it will cross the electric field lines perpendicularly at every point. And this is the case. If this line is a closed curve, like this circle, then it will cross the electric field lines perpendicularly at every point. This is one equipotential line. This is another equipotential line. And yet another one. So you see all equipotential lines created by a point charge. This is minus Q or plus Q, whatever. It doesn't make any difference. And the other thing is equipotential lines do not have any direction. Well, if you think about the electric field lines, when you draw electric field lines, you must always give some direction, but this is not the case for equipotential lines. Okay? The only requirement is the equipotential lines will cross the electric field lines perpendicularly at every point. Okay. Well, this may not be a point charge, but you may have a spherical charge volume, right? This is the source, but it's not a point source. It's a sphere, let's say, of radius r, the diameter 2r, whatever. And if it is, let's say, positively charged, then that means, well, it creates a field distribution around, of course. But since this is, again, a spherical symmetric situation, I mean, as you move along, go anywhere on this source in a circle, having the center, the source center, you will see exactly the same electric charge distribution. That means the source has a spherical symmetry. Whenever you have a spherical symmetry in your charge distribution, this charge distribution will create the same electric field lines with that of a point charge. This is important information. So this will create the same electric field lines, this time since this source is, let me draw this electric field lines as a red line, okay, and these are away because the charge is positive. So again, you may draw the equipotential lines with this configuration, and these lines, equipotential lines, will again be concentric circles. Whether you have a point charge or a spherical symmetric charge distribution of volume, let's say V, whatever, it will create the same equipotential lines, same geometry of equipotential lines. Okay. Now, let me show you another charge distribution. Well, this time, since we are always considering a very nice shape, but this time let's have this kind of non-uniform charge volume. Okay, let's suppose that this is a metal. Okay, it's a volume metal, solid metal. The volume has the metal, and suppose this is charged and positively charged. So we know that if some metals or conductors have some extra charges, these charges will not stay inside the conductor, but they will always be distributed all over the surface only. Okay? If any metal volume conductor has some charge, then these extra charges must always be on the surface. If you ask me how to draw the equipotential lines to this charge distribution of irregular shape, I can right away draw very easily, even though this conductor has no specific symmetry. It has no symmetry, no any spherical symmetry, no cylindrical symmetry, no a plate symmetry, nothing. But I can right away draw equipotential lines to this surface or this charge distribution like this. Let me draw this with a different color. Equipotential lines which is very close to the surface will be like this. Okay. Exactly, it will have the same shape of the surface. And the next equipotential line will be like this. The next one will be like this. The next one will be like this. Okay. You may ask, how can you make sure that these equipotential lines will look like this? Well, it is easy because the surface of a conductor itself an equipotential surface. Because the potential of any conducting material's volume at any point is constant. Everywhere inside the volume, everywhere on the surface. That means the surface of a conductor is itself an equipotential surface. Okay. Well, if this is true, then that means electric field lines will end on the surface perpendicularly. Okay? Because electric field lines and equipotential lines are always perpendicular. So this information is enough for me to draw. This will go like this. This will go like this. Okay. And once you draw these electric field lines, it's easy to draw equipotential lines As you see, every equipotential line crosses the electric field perpendicular at every point. Okay. So next, come back to our question. Well, this problem only gives the equipotential line and extra information that each equipotential line has some potential, and these potentials are given symbolically. If this is V, this is twice, this is third time in compared to this one, and this has a zero potential, this is a negative potential. Okay, so in this picture you also see 1, 2, 3, 4, 5 different charge object. Each has some charge, all right, and 5 paths according to the word to card move a charge Q along each one. Okay, imagine all these points, large points, represents a charge of plus Q. Okay, and the thing is, these lines shows the motion of these plus Q charges, okay, in very different irregular ways. And it says here, rank the 5 paths according to the work required to move a charge plus Q along each one. So for example, for this one, you want to move plus charge Q from this point, initial point, along this path, red one, along this path. First you cross the equipotential line of 2 volts, then you cross the equipotential line of 1 volt, 0, and come back here, just turn, and go back here, somewhere here. Okay, end up on here. So the question says, what is the work required to move this charge along this path? If it says work, then this work in the electrostatic field theory is nothing but the charge Q, whatever the charge you move, because it says it's charge Q, times the potential of the point, end point that you move the charge, this point. Let's call this potential as V final, minus the potential of the point where the charge is initially located. And let's call the potential of this point as V initial. That's it. This is the expression of the work you have to provide to move this charge Q from this initial point where you know the potential of this initial point as Vi to the final point where you know the potential of this final point as V final. So this expression has, as you see, no any information on the path. You see? The path is like this, but it may well be like this. Very complicated path, move along and come to the same point. Even if you move the charge Q along this path or this green path or this red path, as long as the initial and the final points are the same, the work needs to be done will be the same. So the work do not depend on the path you choose, but it depends on the initial and final points only, on the potential of the initial and final points only. Well, this is very important property of electrostatic field theory. Whenever you move any charged particle in a region of space where there is some potential or electric field, whatever, if there is a potential difference, then there must be non-zero electric field anyway. If you move from one point to another, as long as you know the potential of the endpoints, right? The result of the work needed to be done does not depend on how you move the particle, okay? Which path you choose, it doesn't matter, but only it depends on the initial and final potentials of the motion. All right, I think this is clear. So, but we have to make a rank, we have to make a, let's say, a comparative work. Let's call the first one, the first work to be done for the first case as W1. Let me choose W1 is the work to be done to move this charge from potential of 3 volts to this place, to this point. Well, this point is neither on the line, which has the potential 2 volts, right, nor the line which has potential V. So this point must have a potential between 2 volts and 1 volt. So let's make it 1.5. I mean, it doesn't make much of the difference. Let's assign a potential between 1 volt and 2 volts. So let's make it 1.5 volt. And you know the potential of the first point, which is 3 volts. So Q times the final potential, 1.5 volt, minus the initial potential, which is 3 volts. So W1 is minus, let's say, 1.5 Q. Okay. So this much work needs to be done to move this first Q along this path. So what about the second one? The second one, W2. Again, we know the potential of the initial point, it is just V, but the potential of the final point is this one. It's the potential between the 0 and minus V. So let's make this minus 0.5 V, okay? And this is V, this is 0.5 V, but final potential minus initial potential, so Q times final potential minus 0.5 minus, right, minus V, 1V, makes minus 1.5 Q. Well, it goes from a higher potential to a lower one. If a positively charged particle goes from a higher potential to a lower potential, the work needed to be done is negative. It is similar to the case where if you have an object at a certain height, that means in compared to ground, if it is located at a certain height, it has a positive gravitational potential energy, which depends on its height, right? And also its mass. If this goes to a lower location, then it loses potential energy, right? Then, in fact, you don't need to work if you release it, right? The gravitational field does the work itself. So the final potential is negative. The initial potential is the final potential is 0. The initial potential has some mgh. So the potential difference is negative. That means if you release the object, it will go itself. It is a similar case in here. When you release a positive charge at a higher potential, it will move, the charge will move in such a way that it will go to a lower potential by itself. That's why you have minus negative work. If there's a negative work on the result, that means you release the object will go itself, by itself. If these will be positive, then that means to move the charge from this location to here, you must provide some energy to the particle, okay? But this is not the case. Well, if it were like this, if the particle at the second position, for example, the second configuration, if the particle were here, and if I wanted to move to here, then I have to do positive work. But it's the other way around. Just release the particle here, and it goes to a lower potential. It goes by itself. So it's why you have a negative work to do. W1 and W2 is the same. What about W3 for this one? Well, all the way, it goes along the equipotential line. The initial point is at the 2 volts, and the final point is at the 2 volts, so there is no potential difference. V final and V initial is equal to each other, so W3 is nothing but 0. So that's an important property of equipotential lines. If you move a charged object, a charged particle, along an equipotential line, you don't have any work to do. You don't have to do any work. Okay? It's free to move for charges on equipotential lines. So W3 is 0. What about W4? You see, W4 initially is at the 0 potential, right? It moves in some way such that the potential, it changes its potential to a lower value, and then again back to its initial value, and again it goes to a higher potential because it crosses the volt V, the potential V. It comes to 2V, it comes to even higher than 2V, and it goes back to a point where it has the initial potential, which is 0. Again, its initial potential and the final potential is the same, so W4 is equal to 0. Right? You see, it moves in a complicated way. In compared to this one, right? It only goes along the path. The path is always a equipotential line. But for this one, even it ends up this same potential with starting point, same potential, but it goes in a very complicated way, right? But it doesn't matter. The work only depends on the initial and final points. However crazy how crazy this particle go around, if it comes back to the same potential, again, the work done is 0. All right. What about the fifth one? The fifth work. Charge initially is at potential V, and finally it is at potential 3V. The final potential is 3V minus the initial potential is V. 3 minus V is 2V. Q times 2 volts. 2Q volts. So W1 is 1.5Q. W2 is the same, minus 1.5. W3 is 0. W4 is 0. W5 is 2Q volts. So W5 is the largest. W3 and W4 is the same, but lower than W5. And W1 and W2 is the same, but lower than 3 and 4. Okay. So this is the answer to this nice question. It teaches you what the equipotential line is, and it teaches you how to calculate the work to be done to move a particle, a charged object, from one potential to another. You may also write, with this configuration of lines, you may also draw the electric field vectors. As I said, the electric field vectors at every point must cross the equipotential lines perpendicularly. So this is electric field vector, and this one. So not electric field, but electric field lines. Okay, and what about this one? Perpendicular. Okay, so these are electric field lines. If these are the equipotential lines. And these lines are electric field lines. You see at every point they crosses the equipotential perpendicularly. You may go on this to fill the space with the electric field lines. Okay. Well, one extra information that this picture tells you about the comparative strength of the electric field at different places, at different regions. Let me talk about this. Resolve this. If I ask you, compare the electric field strength of this point P1 and the electric field strength of this point P2. Let's call this E1 and E2. Just the magnitudes. Which one is larger, E1 or E2? Okay, so that's my question. Hakan Bal says E2 is larger. And the other guy, Mert, says E1 is larger. I'm just asking the magnitude, not the direction, okay? The strength of the electric field of P1 compared to P2. Anybody else? 2 E2, okay. Two guys says E2 is larger. All right, I think that's all. The answer is E2 is larger, okay? E2 is larger than E1 as magnitude. Why? When you look at the equipotential lines, in the region where these equipotential lines come closer or come denser, okay? Well, look at this one, for example. To change your potential from this to this place, from 2 volts to 1 volt, you go a distance shorter than this one. Imagine the points in question were this point and this point, and just draw a line that connects 2 equipotential lines straight here and here, right? And just compare the length of these lines. Why these lines are drawn passing to the point P1 and P2? Because I'm interested in the electric field strength at these points. Just draw these lines, okay, so that you connect the 2 volt to 1 volt. So this first line, you go a distance larger in compared to that one to change your potential from 2V to V. If you have to go a larger distance, that means, to change your same potential, that means the electric field strength is less than in compared to the place where you go a shorter distance to change your potential, the same potential. You go along these lines, you change the same potential. This line, change the potential V. Again, you go this line, change the potential V. But in the second case, you go a larger distance in compared to this one, or this one, you go a shorter distance, you change the potential, the same potential difference. In that case, the electric field strength will be larger in the case where you go a shorter distance. Or, if the equipotential lines are closer to each other in the region, that means that region must have a larger or a higher electric field magnitude. If the equipotential lines are separated away from each other, then the electric field at this region is lower in strength. Okay. That was another question. Anything else on this? No. Okay. Just I should give a 10 minutes break again. I will again open a new survey. Just answer, rate the second hour from 5 being the most highest number and the 1 is or 2 is lowest number. Okay, how did you learn from my second hour? Just rate it. Okay, again 3 guys responded. I think that's enough. So I'm just pausing the recording. Next thing is, what do we have? What is the condition that if I put a metal into a region of space where in this region there is no non-zero electric field, we have some electric fields, okay? Think about this question. In region of space, we have a non-zero electric field, and into this region we put a metal. What happens? When you can put a metal which has no charge. Okay? Suppose you put a sphere, metallic sphere, which has no charge. As soon as you put this metal onto this region of space, both the electric field lines will be the same. The question. No, because if this is a metal, if this is a conductor, as I said, in conductors, there are free electrons moving inside, right? Well, they are moving, but the net charge is not changing. The net charge is 0. Well, if you put these electrons inside an electric field, when they experience this electric field, they will see a force on them, right? Because whenever you put a charged particle on an electric field, then there will be a force, electrostatic force on that charge, which is in the direction of electric field if it is a positive charge, opposite to the direction of the electric field if it is a negative charge. So as soon as you put this metal, the sum of the electrons, right, will be accumulated on the left-hand side, right? Because electrons, when you put, they will be attracted to the left if the electric field is to the right. This is true. Well, if some of the electrons are going on the left-hand side, then the net charge distribution is changed. In that case, some positive charges must be accumulated on the right-hand side, right? So that the total charge must be equal to 0, right? So as soon as this configuration is there, some of the charges on the left-hand side and some of them on the right-hand side. This is in fact, which is called, what is this called, this phenomena is called the polarization. The charges, when they have no any extra charge on it, the net charge is 0, but some of the charges, electrons, are moving in one side, and when they are moving in one side, since the protons will have no electrons at all around, in that case, on the other side will be plus charges. So this is a polarization, polarized. The metal is polarized. And then, how, the next thing is how these electric field lines will change. You see, some of these lines, electric field lines, enters to the metal perpendicularly, right? But here at some other places, the electric field lines ends on the surface not perpendicularly, but it has some tangential component, right?
It has some tangential component to the surface. If you have this tangential component on the surface, then these charges on the surface will experience electric force, electric field, right? But as I said, in electrostatic equilibrium, the charges cannot move, because if charges are moving, then the currents will be there on the surface. To prevent this happening, the electric field line, which is coming not perpendicularly to the surface, will change its direction so that it is end up on the surface perpendicularly, right? Right, this distribution happens, the electric field lines will change their direction just around the metal, so that all the field lines ends on the surface perpendicularly. If you think otherwise, if the electric field lines do not end on the surface or emerge from the surface perpendicularly, then there will be current flow on the surface, because there will be net electric field on the surface. This causes the electric forces, and the electric forces will move the charges on the surface. So as soon as you put a chargeless metal inside the electric field, this is how the electric field lines deflect, bends, and also how the charges will distribute it over the surface. At some surface and some part of the surface, there will be net electric negative charges. On right at the opposite, net positive charges. But again, the sum of these charges is zero, because initially you have put a chargeless, which neutral metal, and this fact is still the case. The only thing is the charges are distributed not evenly. For this case, if you put into the electric field, there will be some uneven distribution of the charges over the surface. Okay? Again, electric field is equal to zero. Okay? I remind you that even outside the electric field is non-zero. Whenever you put a metal or a conductor inside an electric field, inside the conductor, the electric field is always zero. Whether it is charged or not, whether it is in an electric field or not, the electric field of a metal inside a metal is always zero. There is no exception. Okay? All right. So once you have, I will finish up quickly. Once you have these charges, which is on the outer surface of a conductor, the next question is, what is the local electric field right on the surface? And the electric field, as you know, must always be perpendicular to the conductor. Now you see that there is another important property in electrostatic. For a metal, if you put a metal into a region of space where there is some non-zero electric field, the electric field lines must always end up on the surface perpendicularly. Okay? This is another statement of the electrostatics that you will face in your problems and in your exams. The electric field is always zero inside a conductor, and the electric field lines are always emerging or perpendicular, ending on the perpendicular to the surface of a conductor. Okay, so you can now calculate, if as long as you know the surface charge density on the surface of a metal, you can calculate the strength of the electric field right on the surface. There's a way to do that. Just pick up a Gaussian surface, a pillbox, a rectangular Gaussian surface, right? And you can keep this side as long as small as you want. Okay, this side thing as small as you want, so that one top surface is located just outside the metal, and the bottom surface is just located inside the metal. So the next thing is you calculate the flux through this imaginary Gaussian pillbox. And if you say this has the area top surface as the area A, then it's very easy. because the flux through this area is just electric field strength times A. But what about the Gauss's law says the charge inside must be equal to this flux, charge inside divided by epsilon 0. So the charge inside is just, since this box it crosses the same area on the surface, the same A, because it's a rectangular surface, and the charge inside is just sigma times A, and this is divided by epsilon 0. This must be equal to the flux. So from this, you can easily get the electric field right outside the surface of a conductor is nothing but the sigma divided by epsilon 0. As long as you know the charge density of the surface of a metal, you can calculate the electric field strength right on the surface of the metal. Okay? And this is the case, and this is another nice way of using Gauss's law to calculate the electric fields. Well, inside, always you have electric field is 0. Okay, this is again the case.
Now suppose we have a conductor which has a cavity inside, this empty space, and suppose the conductor has no extra charge on it. So we put a charge, plus charge, Q, into this cavity, into somewhere in the cavity, and the charge is not touching to the inner surface. And of course, because of the point charge, electric field lines will emerge from the plus charge, and they will end on the inner surface normally in a perpendicular direction, that for the reasons that I have discussed earlier. And the question is, what is the inner surface charge density of the conductor? Okay, so this is the question. And although we have no net charge on the conductor, because of the electrostatic attraction of this plus charge Q inside the cavity, we assume that some of the charges will accumulate on the surface, because the other thing is the electric field lines are non-zero right on the inner surface. If there is a non-zero electric field ending on a conductor or emerging from a conductor, then there will be some charges on the surface. There must be some charges on the surface. So for this, again, we will use the Gauss's law. Let's take an imaginary Gaussian surface inside the conductor, so that it contains both the inner surface of the conductor, inner surface of the cavity, and of course the inner charge inside the cavity. And the thing is, this Gaussian surface need not be a symmetric surface, just an imaginary surface. The only condition that this Gaussian surface contains the inner surface and the inner cavity. So if you apply the Gauss's law, first we have to think about the electric flux through this Gaussian surface. But the thing is, whether they are charged or neutral, for all conductors, the electric field inside the conductor is equal to 0. So if there is no electric field lines crossing this inner surface, the imaginary Gaussian surface, not the this inner surface of the conductor, but think about the electric field lines crossing this Gaussian surface, of course it is 0. There is no electric field. The electric field is 0 inside the conductor, so the flux through this Gaussian surface must be 0. Okay, so right away you can write down this flux, or the integral through this surface, is equal to 0. But Gauss' law says if the electric flux is zero through a surface, a closed surface, then this closed surface should enclose no net charge. The Gauss's law says if there is a non-zero flux, then there must be a net electric charge inside this surface. But if the flux is zero because electric field is zero, then the net charge enclosed by this Gaussian surface must be zero. But wait a second. We have a plus charge inside the cavity, so there must be some other charges, and these charges should be negative, so that when you add this total charge in the surface, in the Gaussian surface, they must add to zero. Okay, so the only possibility that for these charges, the extra charges, should accumulate on the inner surface of the metal conductor. So the first charge, this in the expression, the inner charge, the Q plus Q, which is we put originally in the cavity, and because the total of the charge must be zero, there must be some extra charge accumulated on the inner surface of the cavity, because there are no charges inside the metal that we have discussed earlier. No net charge should be in the volume. All the charges for a metal can accumulate, must accumulate on the surface. So the inner surface must contain some charges, some negative charges. Okay, so when you equate this equal to zero, then you can find the total charges in the inner metal surface as minus Q. Okay, so but this can be understood by the Coulomb's law, because when you put a plus charge in the cavity, then this plus charge, because of the electrostatic attraction, it will attract the negatively charged electrons inside this volume to the surface. Okay, so this can be understood by whenever you put the plus charge in the cavity, because of the electrostatic attraction, since there are freely moving electrons inside the volume of the metal, they will be attracted to the inner surface. So inner surface will contain negative charge, which has a total of plus Q charge, the strength of the plus Q charge in the cavity. Okay. So the next question is, well, if you attract these free electrons toward the inner surface, what happens to the outer surface? Well, still there are no net charges inside the volume. If also there is no net charge for the metal anywhere, then if you accumulate some of the negative charges in the inner surface, then by the logical conclusion, the outer surface must contain some plus charges, and the totality of these plus charges must be equal to the negative charges in the inner surface, so that it has a no net charge. So the outer surface also must be charged, and this surface has a total charge of the inner charge Q. Okay, so as you see, whenever you put an extra charge into a cavity, into a metallic cavity, this extra charge will reflect itself on the outer surface of the metal. We have a spherical shell of charge Q, and the charges are all distributed over the surface of the shell evenly. It has a radius of capital R, and the question is, what is the potential inside and outside of this spherical shell. So we will start by picking up a point on the outside of the shell, and let's call this point P, and let's have this distance from the point P to the center of the shell as small r, and the definition of the potential at this point P is given by this line integral, as we have discussed in the lectures, and this line integral from the point P to infinity of the electric field created by this shell. So we know that the electric field created outside of a shell is just the electric field of a point charge of Q, and we put this expression for the electric field dot product with dr. Well, we will take this line integral over this line starting from point P on a straight line going to the infinity on this line that crosses from the center of the sphere. So it's easy because we have KQ, they are constants and can be taken outside integrals. We have dr over r square inside the integral, and 1 over r square integral is just minus 1 over r, and minus 1 over r and evaluated at infinity and r is just 1 over r. So KQ divided by r, where r is the distance of the point P to the center, and if the point P is outside the shell, this is the potential of that point. Next, we will take a point inside the shell, okay, and again let's call the distance to the center as small r, but this time r is less than the capital R, which is the radius of the shell. So again we will use the same definition. We will calculate the potential by using the line integral of the electric field from this point R to the infinity. But we have to break this integral into two terms, because when you go on this line starting from point P inside to the far distance, you crosses this special border of the shell at r is equal to capital R. So we break the integral into two parts. When first take the integral from r to the capital R, okay, which is the radius of the shell, plus from this capital R to the infinity. So we have two terms now. Why do we have to break up the integral into two pieces? Because the electric field is not the same everywhere. For the points inside the shell, we know, we already calculated this by using the Gauss law, the electric field inside a charged shell is equal to 0. So the contribution from the first term, first integral, will be 0, because from r to capital R, the electric field inside the shell is 0. So we are only left with the second integral, and this integral is again easy, just like this one. It can be taken very easily. It is just k times, or 1 over 4 pi epsilon 0, q divided by the capital R. So this is true for every point inside the shell. For every point inside the shell, the potential is just this term, is kq divided by capital R, because the electric field is equal to 0 wherever you go inside this shell. If you have a charge in your pocket, wherever you go inside the shell, you will not experience any force. If you don't experience any force, that means you don't change the potential, and the potential just the same as the potential of any point on just the surface. Okay. So this is the graph of the potential for all points inside and outside the shell. So from r is equal to 0 to the capital R, where this is the radius of the shell, the potential is just constant. It is a constant value of this kq divided by r, and right from outside it drops as 1 over r to the infinity. So at infinity the potential is again 0. You can easily check, because for all points located at infinity the potential is always 0. So you can check this from this expression.
Let's picture the problem. So we have two concentric cylinders, and the inner cylinder is a metal rod which has a radius a, and the outer cylinder is a shell which has a radius b, and between these two cylinders we have an empty space. So the inner cylinder has a charge density plus lambda, and the outer has minus charge density minus lambda. They have the same charge per length in the in this direction. So to calculate the electric field, we separate this problem into three regions. The first region is the inner region of the metal rod, but since we know that inside each metal, every metal, electric field is 0, so you don't need to calculate the electric field. It's right away just E is equal to 0 inside when R is less than A. And for R between A and B, we pick a point which has a distance R to the center of the axis of the cylinders, and we choose a imaginary Gaussian surface. Because of the cylindrical symmetry of the problem, this Gaussian surface will be a cylinder. Let's take it as a height h, and of course the radius is r, because this is the distance of the point that we want to calculate the electric field to the central axis. So what we do is, first, of course, we calculate the electric flux through the side surface of the inner of the S1 surface, this Gaussian surface cylinder. But the thing is, the area vector in every point on this side surface is perpendicular to the surface, and because of the symmetry, the electric field will be in the same direction because we have a positive charge inside. So the flux is this closed integral through the surface S1, and we don't even think about the top surface and the bottom surface of the cylinder, because the electric field and the area vectors are perpendicular to each other in these top and bottom surfaces, so they contribute a zero flux. So the only flux contributed is coming from the side area of the cylinder, and it is just the strength of the electric field times the side area of the cylinder, which is 2 pi r times h. And by the Gauss's law, this flux must be equal to the charge inside divided by epsilon 0, but since the height of the cylinder is h, the amount of charge which resides inside this Gaussian surface is just h times lambda. So this is the total charge inside, and from this we can easily solve for E, and E will be lambda divided by 2 epsilon 0 times R. So that means in the region between these two cylinders, the electric field will decay as 1 over R as you go away from the central axis. So this is the expression in between. The next question is, what is the electric field when you pick up a point which is outside the spherical shell? So that means the radius will be larger than B, because B is the radius of the outer shell. And again, we follow the same schedule, that we choose a Gaussian surface, which is a cylinder that passes through the cylinder, that passes through the point that we calculate the electric field, and everything is the same, and the flux is the same with that one, E times 2 pi r h. But when you come to the charge which resides inside this blue Gaussian surface, it will be of course 0, because we have plus lambda charge distribution in the inner core and minus lambda in the outer shell. So if you add them, you will have a 0 net charge. That means the electric field outside these cylindrical shells, the cylindrical metals, conductors, will be equal to 0. So the next question is, what is the electric potential at all points? Well, the electric potential at right on the surface of the outer shell, we claim that it is equal to 0, because the potential at infinity is 0 by definition, and since there is no electric field outside, then if you bring a charge from infinity to the surface of the outer shell, there is no electric field, so the electric field line integral will be 0. Then we will have the same potential, we must have the same potential at that of infinity at the surface of the outer shell. So this is the reasoning that we should have the potential of the outer shell is equal to 0. And next, let's choose a point in between these two cylinders, and the R is in between A and B. So what is the potential of that point which is inside in between these cylinders? Let's take this point as a distance R to the center, and well, since we always define the potential difference, well, let's choose a potential, a point which we know the potential. Let's choose the potential difference between this point VR and the potential of the outer shell VB. Since we know the potential of VB, it's just a 0, and the definition goes like the potential between any 2 points is nothing but the minus of the line integral between these 2 points, line integral of the electric field. So we put R in the upper limit and the B in the lower limit. And the thing is, we know what the electric field inside. We know what the electric field in between these two cylinders. We already have calculated from the Gauss's law. So next, is just put VB is equal to 0 because of the reasoning that we previously considered. And then the next thing is just replace, interchange these limits, put B to top and R to bottom, and then changes the sign of the integral. And inside we have E dot R. From E dot R we have 1 over R integral dr over R, and it is very easy to take because 1 over R integral is just logarithm, natural logarithm. And if you put the limits of the integration, we will have the final expression lambda divided by 2 epsilon 0, 2 pi epsilon 0 times the natural logarithm in parentheses b divided by r, where r is the point in between these two cylindrical shells. And of course the rest is what is the potential of any point on the surface of this inner cylinder, metal cylinder. Just put R is equal to A in here. And then the potential will be all the same through the volume of the inner cylinder because there is no electric field. The electric field is 0. So whatever the potential we have at the surface, we will have the same potential in the inner region. The charge rod is on the x-axis and extends from x is equal to minus a to the x is equal to plus a, which is a length of 2a, and the total charge is q. So the question is, what is